don't understand what happened in 1995.
You need to get educated in music.
I know we didn't start the
You need to get educated in music.
I am educated in music.
All right, today we're going to start talking about limits as x approaches infinity. Okay, so what that means is as x goes forever to the right or as x goes forever to the left. Right? Most of the time, okay, when we're for the problems that we're going to look at, that means we're going to be looking at an asymptote. Right? So for today, all we're going to look at are horizontal asymptotes. Tomorrow, then, we'll look at vertical asymptotes. But today, we're going to look at horizontal asymptotes. Right? We want to know limits as x approaches infinity. Okay, so the notation for that, right, we're just going to say the limit as x approaches infinity for some function, right? Or it could be as x approaches negative infinity. And if we're saying as x approaches positive infinity, we're going to the right, negative infinity, we want to know what's going on as we're going further and further to the left. Right? So let's take a look at this idea graphically first. Right? So if I've got this function right here, okay, I want to know the limits as x approaches both positive and negative infinity. So those are two different things. Right? So I'll say the limit as x approaches negative infinity, calling this h of x, and the limit as x approaches positive infinity for my function. Okay? So if I'm looking at this graph, so let's do as x approaches negative infinity first. That's saying, what value, what y value am I getting closer and closer to as I go forever to the left? Negative 1, right? Because that's where this asymptote is. So the limit as x approaches negative infinity is equal to negative 1. Right? Now, this would only equal a finite value if we have an asymptote. Right? I mean, it's certainly possible that there is no asymptote here and the function, just keeps going up forever like that. Right? Then we would not have a finite value here. Okay? Then we could say the limit is either positive or negative infinity. Okay? But most of the problems we look at are going to have asymptotes. What about as x approaches positive infinity? 5. Right? Okay? This of the function that's going to go forever to the right is getting closer and closer to a y value of 5. So the limit as x approaches infinity is just equal to 5. Okay? So graphically, and hopefully this makes some sense, right? We're just looking at the value that we're approaching, the y value that we're approaching. Right? Now, I mean, like I said, if there wasn't an asymptote here and this piece of the function just went like this, right, we would just say the limit as x approaches infinity of h of x is equal to positive infinity, like that. Okay? So if there isn't an asymptote, and if it just keeps going up forever or down forever, we can use positive and negative infinity as answers. Any questions on that idea graphically? All right, then let's start thinking about these algebraic. But first, we want to think about this question. What does 1 over infinity equal? Say what? All right. What about 1 over, we don't have to think about infinity, but think about a really large number. What is 1 over a million really close to? 0. So what's 1 over 10 million? Even closer to? 0. Right? So this idea here, 1 over infinity, is essentially equal to 0. Okay? That's going to be an important idea for what we're going to do here algebraic. Okay? Now, what about, 5 over infinity? Would that be the same idea? Sure, right? I mean, if we think about some huge number, right, 5 over a million or 5 over 10 million, that's still going to be really, really close to 0, right? Essentially as close to 0 as this is, as we get closer and closer to infinity, right? So if we just have some finite value up here over an infinite value, that's going to be essentially equal to 0, right? So that's going to be a key idea here. So jot that down. 1 over infinity, or a over infinity, is equal to 0. Okay? So if we want to find a limit algebraically, okay, as x is approaching positive or negative infinity. So I'm going to jot down an example here as we go. So let's say I want the limit as x approaches infinity of, I don't know, let's start with x minus 7 over x squared plus 2x minus 3. Okay, something like that. Okay. If I've got a rational function like this, okay, where both the numerator and denominator are polynomials, what I want to do is divide every single term by the highest power that appears in either the numerator or denominator. Okay, so in this example, the highest power that I see is second power. Okay? So what I'm going to do is divide every single term by x to the second power. Okay, so this is going to end up looking like this. As x approaches infinity, I'm going to divide everything by x squared. And so x squared over x squared plus 2x over x squared minus 3 over x squared. Okay, and then we want to simplify each of those as far as we can. So, let's see, x over x squared would just reduce to 1 over x, right? Forgot my limits. Okay, now, when I'm showing you this, the first few times, we're going to write all this out and show a lot of work, but as we get the hang of it, we're not going to need to write all of this out. Okay, so x over x squared would just reduce to 1 over x. Okay. 7 over x squared isn't going to reduce. X squared over x squared would just be 1 plus 2 over x minus 3 over x squared. Okay, you okay so far? Almost. Okay, so now we want to think about plugging in infinity. Okay, and we want to use that idea that we just talked about, that 1 over infinity, or any finite value over infinity, just is equal to 0. Right? So if I plug in infinity into this, 1 over infinity, that's going to go to 0. Right? So I'm just going to note that. Okay, just kind of say this is going to go to 0. How about 7 over x squared? That's going to be the same idea, right? That's going to go to 0. Well, there's no x value here. Right? So that's just going to stay 1. How about 2 over infinity? 0. Minus 3 over infinity squared, also going to go to 0. So we get 0 over 1. What's 0 over 1? Just 0, right? So my answer, the limit as x approaches infinity of this function is 0. Okay. All right, now, if you think back to pre-calc, you talked about rational functions. I think you talked about 3 rules, okay? Saying, well, if the power in the numerator is greater than the power in the denominator, if the powers are equal, or if the power in the denominator is greater. Those ring a few bells at all? Remember those rules? Okay. This is essentially doing the same thing. Okay. If we look back to our original function, the power in the numerator is less than the power in the denominator. Right? means that the denominator is going to be growing faster than the numerator. Right? So if I'm plugging in some huge value, right, as we get closer and closer to infinity, the bottom is going to be much larger than the top. Okay? Meaning the whole fraction is going to go to 0. That means that this, if I graphed this, the horizontal asymptote would be at 0. Okay? We okay with that one? Alright. So let me throw another one up here. So how about the limit as x approaches infinity of, I don't know, 2x squared minus 7 over 3x squared plus x minus 2. How about something like that? Okay, you guys try this one here. Okay, see if you can figure out what is going on here, what this limit will be equal to. So try dividing every single term by the highest power and see what you end up with. Yeah. So you mean when you divide? So I think it's going to be easiest if you just divide everything by x squared. Yeah, I guess in this example, neither of those had a leading coefficient. Yeah, so when we divide by the highest power, we're just going to take the x. So in this case, I would just divide everything by x squared. Did we get 2/3 for that one? Okay. Feeling okay with this process so far? Alright, so let's do one more example here. I'm going to erase these. Alright, how about limits as x approaches infinity of 4x cubed plus x over 3x squared minus 2x plus 1. So when we do our algebra here and our simplifications and plug in infinity, I think we should get 4 over 0. What does that mean? What happens if we get something like that, 4 over 0? And so, I mean, everything we've done so far, right? If we get something like this, a number over 0, that means the limit doesn't exist, right? What this actually means, if we think about here, the power in the numerator is greater than the power in the denominator. That means the numerator is growing faster than the denominator, right? It's just going to keep growing. So it's not approaching a finite value, right? So you'll see this written a couple of different ways, okay? We can say that this is unbounded, okay, meaning it's not approaching a finite value. Or sometimes we'll just say this actually equals infinity. Okay? So we might say it's unbounded or it equals infinity. Okay? So I mean this just means if we get something like this, it's just growing forever. It's not approaching a finite value. There is no asymptote. Okay? So I mean we went through each of the 3 possibilities, right? Either we get 0, we get a different value other than 0, or we get something that's unbounded. Right? So any questions on this idea?
My hair.
All right, then it's kind of small. Now, I kind of started mentioning, okay, how we can think about this a little bit intuitively. Okay, we want to think about plugging in infinity, right, whenever we see a value, or whenever we have a function, and think about, well, does the numerator or denominator grow faster? Right. So here in this example, if I've got the limit as x approaches infinity of x cubed over e to the x, if I think about plugging in a big number, I mean even just 100, would 100 to the 3rd power be bigger or smaller than e to the 100th power? Right? Would the numerator be growing faster or the denominator? The denominator. Right? If I'm raising something to a really large power, that's going to grow a lot faster than if I'm just raising a large number to a finite power. Right? So 1,000,000 to the 3rd power over e to the 1,000,000th power. This is essentially, okay, going to be a smaller number over a really big number. Right? So this is going to be a over infinity. Right? So what would the value of this limit be? Right? If the denominator is growing much, much faster than the numerator. 0. Right? So ones like this, much later on in the year, we will have a very concrete way of solving these. Okay? But for now, we're just going to have to think about these intuitively. Okay? We have to go through half the year and learn a whole bunch of calculus before we have a concrete way of solving these limits. Okay? But for now, we can still think about them intuitively and think, well, if I plug in some huge number, the denominator is going to be growing much, much faster than the numerator. Right? So in this case, I know that this is going to be 0. Right? So it's kind of weird to think about right now. Right? But we will have a concrete way of doing these about halfway through the year. Right? Are we okay with that idea for now? Right. Then let's, there's my function. Let's try this one here. Okay? So it says identify all horizontal asymptotes. Okay, that's the same thing as finding the limit as x approaches infinity or x approaches negative infinity. Okay, so let's try this one here, and then we'll also look at the graph and the table for this to kind of get all vantage points of this function and what's actually going on here. Okay, so just try this one here. This one is actually simpler than the examples that we did before. It might even be to a point where you can do it without writing down a whole bunch of work.
Yeah.
Positive. Yeah, so for this one, right, if we plug in negative infinity, what's 1 over negative infinity? Still 0, right? So in this case, yeah, both of these would be equal to 1. Yeah. So, and I could actually, instead of writing it out twice, I can actually just write this, in this case, to show that it's the same either way. I can write as x goes to positive or negative infinity. Now this isn't always the case. Okay? Sometimes we will be approaching different values as we go to the left or to the right. Okay? But in this case, we are approaching the same value. Okay? And it should be positive 1. Now, let's take a look at graph. Okay? So this is what this graph looks like. Right? And we can see that in both directions, we are approaching our asymptote of positive 1. Now, if we looked at this from a table as well, okay, we can see that as we go really far to the left or really far to the right, I'm getting closer and closer to the value of 1. Okay? To the left, I'm approaching 1 from the bottom. To the right, I'm approaching 1 from the top, and I'm getting closer and closer to a value of 1 both directions. Okay? So, I mean, we've talked about limits graphically, limits from tables, limits algebraically. Okay, this just kind of brings all that together in this example. Okay. So, any questions? All right. Then let's think about maybe. There we go. We're actually not going to talk about the sandwich theorem today. Right? We're just going to do this one kind of the way that we've been talking about. Right? But here, throwing in a trig function. Right? We've got the limit as x approaches infinity of cosine of x over x. Now this one, we're not really going to be able to do algebraically right now. Right? But we can try to think about it intuitively. Right? Again, later on in the year, we will have a way to do this algebraically. Right? But for right now, we just kind of have to think through it. So, if I plug some huge number in, well, obviously the bottom would be going to infinity. Right? If I plug in infinity to the bottom, that's going to be infinity. What if I plug some huge number in for cosine? What does the cosine function do? What does the graph of cosine look like? Yeah, it just goes like this, right? Bounces back and forth between -1 and +1. So even if I plug in some humongous number, right, if I go really, really far to the right on the number line, I'm guaranteed that that's still going to be between -1 and 1. Right? The y value will still be between -1 and 1. So here, if I know that no matter what value I plug in, right, I can plug in 1,000,000, and I know it's going to be somewhere between -1 and 1. This is essentially going to be approaching what value? If I've got something between -1 and 1 over infinity, 0. Right? I've got some small number over over some humongous number, this is going to be approaching 0. Okay, so for problems like this, okay, this is the thought process. And this is actually what the graph ends up looking like. Okay? It bounces back and forth across the x-axis, but it gets smaller and smaller as we go and actually approaches 0. Right? So, I mean, we don't have to have an asymptote that our graph doesn't cross. In this case, we have an asymptote that the graph actually crosses an infinite number of times. We're getting closer and closer to a value of 0. Right? So we would say the limit as x approaches infinity in this case is equal to 0. Right? And we can see that from the table, we can see that from the graph. Why this is so related. But as we get closer and closer to infinity, and plug in bigger and bigger numbers, we get closer and closer to 0. Alright? Now, these, you don't, I mean, if you want to, you certainly can, but you don't need to write all these down. Okay, these are the rules that we already wrote down, okay, for finite limits. Okay, this is just saying they all still apply for infinity. Right? So if I've got two functions, and I say the limit as x approaches infinity of some function is 2, and the limit as x approaches infinity of some other function is 3, then the limit of their sums as x approaches infinity would be 5. Right? This is just saying all those rules that we already talked about still apply if we're saying x approaches positive or negative infinity. Right? So, I mean, if you want, you can certainly write these down again. Okay, we're saying it applies for addition, subtraction, multiplication, division. It's coming. We got multiplication, constant multiple. Right? We just multiply it by a constant, by like 5. We use division, or if we raise to a power. Right? So all those rules still apply as we're saying x approaches positive or negative infinity. All right, one last idea for today. Okay, we're just going to throw some square roots in. So this is the same idea. We're saying the limit as x approaches infinity. We've got some function over some function. Right? I actually want to use the exact same idea, okay, that we talked about to find limits as x approaches infinity. I want to divide every single term by the same thing. Now, if I've got a square root, though, I have to think about what's going to be equivalent to what. Right? So, the highest power, right, I'm going to think about as x squared. Now, x squared, if I want to write that inside of a square root, x squared is equal to the square root of what? X to the 4th power. Exactly. So what I'm going to end up doing for this, everything that's inside of the radical, I'm going to divide by x to the 4th. Everything that's outside of the radical, I'm going to divide by x squared. So what that's going to look like is this. Up top, I'm going to have 16x to the 4th over x to the 4th minus 3 over x to the 4th, like that. Then down here, I'll have 2x squared over x squared plus 3 over x squared. Right. Then we can do some simplification. So up here, I will have square root of 16 minus 3 over x to the 4th. Down here, I will have 2 plus 3 over x squared. Okay. Now we can think about plugging in infinity and seeing what values go away. And well, if I plug in infinity, this is going to go to 0, and this piece is going to go to 0. Exactly. So I'm left with then the square root of 16. 2. The square root of 16 is just 4. 4 divided by 2 is 2. So whenever we have a square root like this, okay, the key is just making sure that we're dividing everything by something that's equivalent. Okay? Making sure that we're dividing everything by something that's equivalent. You okay with that idea? Alright, you guys try this one then. Okay, try the middle one here. So, whenever
If you take the square root of x to the 12,
will, because so think about it like this, right? The square root is the same thing as the 1/2 power, right? Whenever I've got a power to a power, I multiply them together. So we're going to do this last one together because something a little bit different happens on this one. Okay, so did we get 3 for this middle one here? Okay, so we use the equivalent factor here of x to the 6th is the same as the square root of x to the 12th. All right, now, on this one, we did have something a little bit different. We had as x approaches negative infinity on this one. Okay, on this first one, we had as x approaches positive infinity. On this one, we had as x approaches negative infinity. Now, that actually didn't matter. In this case, we did this one the exact same way because we had an even exponent, right? Positives and negatives don't matter if I've got an even exponent, okay? Because if I've got, for example, negative 2 to the 6th power, well, that's going to be a positive answer. Right? Negative 2 times 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 negative 2 is positive 64. Now, if I've got an odd power, though, okay, something a little bit different is going to happen. So if I look at this one, my largest power is x to the 5th. If I'm approaching negative infinity, okay, as x approaches negative infinity, x to the 5th is not going to be the exact same as the square root of x to the 10th. Okay, if I think about plugging in a negative value here, if I plug in negative 2, I'm going to get negative 32. Right? Negative 2 to the 5th power is negative 32. But if I plug negative 2 in over here, okay, the square root of negative 2 to the 10th power is going to be a positive value. So if I'm approaching negative infinity for an odd power, I have to throw a negative sign out in front of my equivalency factor here. way, I just made up that term. So don't actually use that. That's not a real thing. Alright, so if I'm approaching a negative value and I have an odd power, okay, that's the only case where we actually have to use a negative here. Okay?
The negative sign in front of everything that's in front of there under the graphical or just the N.
So the easiest way, let's write all this out and I will answer your question as I write it out here. So when I use this factor, I divide everything by these factors. The easiest way to do this, to show that we're dividing everything by a negative x to the 10. It's just going to be to bring a negative out front like that. Okay, so you can just show that you're dividing by a negative x to the 10th by pulling a negative out in front. Okay, that's going to be the easiest way. So then, the algebraic process is the same as what we've been doing. Okay, we want to figure out what's going to reduce. So as x approaches negative infinity, you get 1 plus 4 over x cubed over negative square root of 1 plus 8 over x cubed. Then as we think about plugging in negative infinity, these two things are going to go to 0. We're just left with this 1 over negative square root of 1, which just ends up being negative 1. Okay. So any questions on limits as we approach infinity?